section 3.5, we're not going to look at higher order derivatives. So for the things that we've done so far, we have just been taking the first derivative, but you can take the first, second, third, and it goes on forever. So if the first derivative is f prime of x, we can write these out with a different notation. So the second derivative would be f double prime of x. The third derivative would be f triple prime of x. And then after the third derivative, they stop using primes because it would be really hard to like count how many hash marks. But you can't just use numbers because then it looks like an exponent. So to take care of that, then they put it in parentheses. So the fourth derivative is f4 of x, and the fifth derivative would be f5 in parentheses of x, and it goes on. We also have been using the y notation a lot. So first derivative y prime, y double prime, y triple prime, and then the same thing. After 3, we put those in parentheses. And then we also look some at the dy dx notation, which just means we're taking the derivative of y with respect to x. The second derivative is d2y dx2. The third derivative is d3y dx3. And so on. We don't need the parentheses for that notation because dy dx is a derivative, so it's very clear, versus if you just had f of x. Alright, so let's take some derivatives. I want to find the first 5 derivatives. So my equation is y equals x to the 5th minus 2x to the 4th plus 3x to the 3rd plus 5x squared plus 10x plus 10. So that's the original function, my first derivative, y prime. That 5 comes out, so it becomes 5x to the 4th. Multiply the 4 down, we get 8x to the 3rd. And then 9x squared, and then 10x, and then 10, and then the derivative of this last 10 is just 0. So that's my first derivative. My second derivative, multiply the 4 out with the 5, we get 20x cubed minus 24x squared plus 18x plus 10, and again that derivative of that last 10 is a constant, is 0. The third derivative, I get 60x squared minus 48x plus 18. My fourth derivative, I get 120x minus 48. And then the fifth derivative is just 120. The sixth derivative would be 0 for this one. So we're going to talk about some applications of when you have higher order derivatives in just a bit. Alright, here's another one. I want to find the third derivative. So I have f of x equals 9x to the 1/3 power. And I want to find f triple prime of x. So first derivative, f prime of x, that 9 times 1/3 gives me 3x, and then when you subtract 1 from 1/3, you get negative 2/3. The second derivative, negative 2/3 times 3 gives me a negative 2, x to the negative 5/3, because negative 2/3 minus 1 gives me a negative 5/3. And then the third derivative, I get 10/3 when you multiply that, x to the negative 8/3 when you subtract 1 from that exponent. Right here I want to find the second derivative. So I have y equals 2x squared plus 3, and that's to the 3/2 power. So my first derivative, I'd get the chain rule, so I get 3/2, 2x squared plus 3 to the 1/2, because we have to subtract 1 from that exponent, and then times that derivative of 2x squared plus 3, which gives me a 4x. So I can at least multiply the 3/2 and the 4x together, and that will give me 6x times 2x squared plus 3 to the 1/2 power. Now the second derivative. Now I have to use the product rule and the chain rule. So I'm going to leave that 6x, and then the derivative would be 1/2 2x squared plus 3 to the negative 1/2 power, and then the derivative of 2x squared plus 3 gives me 4x. For the second one, I have the 2x squared plus 3 to the 1/2 power, and then the derivative of 6x just gives me a 6. So I'm just going to clean it up again just a little bit. And the 6x and the 4x and the 1/2 multiplied together, I get 12x squared times 2x squared plus 3 to the negative 1/2 plus 6 times 2x squared plus 3 to the positive 1/2. And if you wanted to change this negative 1/2, you could bring it into the denominator and make the square root. And then the same with this one, you can write the square root if you want. I tend not to do that because I like to just leave my fractional exponents, but you will see word problems out like that. Alright, so I want to do one application problem here, and that's when we talk about the position function. So S of t is a position of an object in any particular time, t. And if I want to know the velocity, which is instantaneously how fast this thing is going, then I take the derivative of the position function and it gives me the velocity. I also want to know how things are accelerating. So my last function is acceleration. And how I get that is I can take the derivative of the velocity function, which is just the second derivative of the position function, and that gives me the acceleration function. So let's say we have an object moving on a track, and we're given that position function S of t is equal to 4t squared, and this domain is between 0 and 10 seconds. So if I want to know the velocity at any particular time, then I take that derivative and I get the velocity as 8t, and I can evaluate it for anything between the 0 and 10 seconds. If I want to know the acceleration, then I'm going to take that velocity function, which we just found is 8t, and take its derivative, so 8. So the acceleration for this object at any time is equal to 8.